Now let's talk about piecewise linear interpolation, where we play connect the dots with the data points. The setup, once again, is an ordered list of nodes, which we number t0 to tn. And going with the nodes, we have data values from y0 to yn. By definition, inside the interval from tk to tk plus 1, the interpolant is linear, so it's determined entirely by the two endpoints of that interval, and it's easy to write out a formula if we want one. Now the formula itself for p changes depending on which interval you're in. That's what we mean by a piecewise definition. In the last section, we took a look at the cardinal functions for piecewise linear interpolation. That's 1 at one node and 0 at the others. These are also called hat functions or tent functions for graphical reasons. The hat function is characterized by being 1 at node tk and 0 at all the other nodes. It can be shown that any function that is piecewise linear and continuous over the whole interval, from t0 to tn, can be written as a linear combination of these hat functions. It also turns out that there's no way to find a smaller collection of functions that have the same property. And we say that the hat functions form a basis for piecewise linear interpolation. They're actually a very convenient basis for interpolation in the sense that there's no real need to solve for the coefficients, ck's, in that expression. We just put in the data values in their place. Let me expand on that for a second. When we started out with polynomial interpolation in Chapter 2, we wrote down a polynomial with undetermined coefficients. Then we imposed interpolation conditions, which led to a linear system that we had to solve for the coefficients. We didn't use this language at the time, but we were using a basis that were the functions 1, x squared, and so on. Now the process is the same, but we're using the hat function basis instead. The details change when we write down the interpolation conditions. Then we find that because of the cardinality conditions on the hat functions, the sum collapses down to a single value. All the other terms are 0. In fact, the linear system, in this case for the coefficients, just has an identity matrix, so there's nothing to solve for. The coefficients are the same as the data values. So we can just write down the interpolant directly, which is a nice advantage. Remember that in general interpolation, the condition number can depend on the nodes as well as the type of the function, or the basis. Now, as we wrote before, let's use the squiggly I to denote the operator that maps a data vector to its piecewise linear interpolant. There was a theorem in the last section that gave upper and lower bounds on the condition number of I, but we can actually show that it's exactly equal to 1. So let's suppose we take our data vector y and we perturb it to y plus z. That changes the interpolant. Thanks to the linearity, the change in the interpolant is just I applied to z. So if we can show that the norm of I of z is less than or equal to the norm of z, then the condition number, which is the ratio of the two norms, must be less than or equal to 1. Showing the opposite case that it's greater than or equal to 1 is much easier, and I won't put it here. We'll use the infinity norm both on the function I of z and on the data vector z. So the infinity norm of I of z, by definition, is the maximum of its absolute value. We can easily bound this from above using the triangle inequality. But when we look at the absolute value of the zk's, each one is less than or equal to the maximum of all of them, and that's the infinity norm of z. So if we replace them all by the infinity norm of z, the thing can only get bigger. Now this remaining sum, there's an exercise in the book to show that that sum is equal to 1 for all values of x. The notion of accuracy is a little subtle here. For one given set of nodes and values, there's no inherently one right way to interpolate them. So we need some context. One of the things that we'll be doing a lot with interpolants is using them as substitutes for other functions that we know only by their values. So in other words, let's suppose there's an underlying nice function f that provides the yk values for us. When we do that, we can ask about the difference between the original f and the piecewise linear interpolant p. And this difference you could think of as now an error in the interpolation. We want the error to shrink as we pack the interval with more and more nodes, which means that as n goes to infinity. The simplest case to think and talk about is when the nodes are equally spaced, separated by a distance h. So h must be proportional to 1 over n. Now the limit we seek, n going to infinity, is the same as h going to 0. Let's let Pn be the interpolant we get when we use n plus 1 nodes. As described in the exercises, there's a theorem we can prove giving an upper bound on the difference between f and Pn. This bound is a constant m times h squared, where m is the maximum of the second derivative of f. In most situations, we don't actually know m, we just know that it's there. And what's important is that the error is on the order of h squared as h goes to 0. We call this second order convergence. So for example, if we cut h in half, we should expect the error to get smaller by a factor of 4. So here's a simple smooth function that you can see here from over the interval 0 to 1. And I'm going to set this up for piecewise linear interpolation. So here I'll choose 9 nodes, which means n is equal to 8. And y will be the value of f at those nodes. So that's our data vector. PLInterp is the function from the book that creates the piecewise linear interpolant. So the output of that is a function. So now p is a function like any other, a function of x. And we can add that to our plot, and so you can see how you get the piecewise linear interpolant at those points. Now for our purposes, it's going to be a little bit more instructive to look at the difference or the error between them. And so you get this weird looking plot, but right, it has to go to 0 at all the nodes, and it's only piecewise smooth because the interpolant is piecewise linear. So now if I were to increase n and repeat the interpolation process, so now n goes to 16, then you can see that the error gets smaller. In fact, since I doubled n, by going from n equals 8 to n equals 16. Second order convergence says that this error should get kept by about a factor of 4, which seems to be what's going on. To be a little bit more quantitative about that, I'll run an experiment here for many different values of n. I have to estimate the error. I can't compute it exactly, and I'll do that just by sampling the error at a whole lot of points in the interval and taking the max over that. So I construct the nodes, construct the interpolant at those nodes, and then I find the maximum absolute value of the error at my values of x. So when you do that, you do see, for example, here I've chosen n so that it keeps doubling. So here you do see that it's gone from about 0.004 to 0.001, and then from there to 0.00025. So that is consistent with going down by a factor of 4 for each doubling. Or if we want to see second order convergence, since error is proportional to h squared, h is proportional to 1 over n. It's the spacing between the points. So the error is proportional to n to the minus 2. That means we want to show it on a log-log graph, and we should get a straight line at least as n goes to infinity. And in fact, we get something that's extremely straight even for smaller values of n.